Hello, this is our COP4533 project or algorithm abstraction project. I'm Alan Wang.
I'm Derek Mo, and let's get started.
So this is just a table of contents for our project. So we'll first start with the algorithm overview, followed by the implementation details, then the
Performance analysis, as well as finishing off with the strengths, limitations, and improvements for our algorithm.
yep. So this is the algorithm overview.
First things first, let's talk about the problem. We chose to focus on the interval scheduling problem, which has the situation where there are n meetings throughout the day and you want to be able to schedule the most amount of meetings. However, we added our own little twist to the problem, which is each meeting has its own priority. So, in conjunction with wanting to schedule the most amount of meetings, we also want to make sure that we are prioritizing the most important meetings. So, for our algorithm, we must consider each meeting's ability to allow for more meetings along with its priority.
Yep. So I'll talk about the real world use. So in the real world, there's of course meetings, and each meeting has a limited time. So our algorithm helps users prioritize these meetings within a limited time by maximizing scheduled meetings and reducing overlap. So if a business wants to get as many meetings done while also getting the most important meetings, our algorithm is perfect for this. It's especially useful for businesses managing conference room usage and organizing meetings by importance. So this basically maximizes the meetings throughout the day and helps the business run optimally.
Yes. So how our algorithm runs is first we sort the meetings by priority, and then we look through them. And then after we sort by priority, we check the earliest end time. So let's say if there was a tie in priority, we then prioritize after that which meeting ends earlier to allow for more meetings to occur throughout the day. And then we also ensure that the meeting that we're currently talking about is within the boundaries of our day. So if we were scheduling meetings from hour 0 to hour 20, and we had a meeting that was going to run till like hour 30, we would ignore it because it's outside of our boundaries.
Yep.
So the solution to this problem is our solution to this problem is a greedy solution. And that's because we aren't really considering what's happening beforehand or after. We're just looking at the current meeting and just determining what is most optimal right now, which is basically the definition of a greedy algorithm.
Mm-hmm.
So at each meeting, we check the meeting with the highest priority, and then, like mentioned earlier, we also sort by the earliest finish time in order to leave more time for future meetings.
Yeah. So the second part of our presentation is the implementation details. So as mentioned, the GitHub is linked in our assignment. If you click the GitHub, this is the README. So I'll basically explain how to do the README and how to run our code, as well as an example input. So basically make sure that you can do a git clone of it, or you can make sure the following files are in the same directory. You want maximum meeting times.cpp, makefile, as well as input.txt. Once they're all in the same file or directory, then open your terminal, cd into that directory, and then run make, followed by make compile, and finally make run. So once you finish these three make commands, the code will run and it will output the answer. So I'll talk more about the input format, which is in input.txt. So as you see in the bottom, there's the example input. You see with the 1060, 1020, 33. So the first line contains two integers representing the start and end of the time interval. So let's say this is a business, so it would start at 10, it'll end at 60. So that's when the meetings can last. And then each subsequent line represents a meeting in the format start time, end time, and priority. So as you can see, I'll just run through it real quickly. The start time would be 10 to 20 with priority of 3. The next one would be 10 to 15 with a priority of 4. So just looking at those two examples, you can see that 10 to 15 should be the answer because it's a higher priority, and 10 to 20 does not fit that interval because it's already taken. So I'll talk more into the code breakdown. So if you can see in the top right, this is the data structure we decided. We decided to do a vector of pairs of pairs. We thought this was more optimal since it'll store all the data effectively, since it'll be all in a vector format and it'll be easy sorting. So how the pair would work would be the first number would be a pair with the start date and end date, and the second value of the pair would just be the priority. And since it's in this data structure, it'd be easy to do a comparator operator. So if you see like the compare priority end and start, we basically have this function that sorts this vector. It first checks whether or not it first sorts it by priority. So like if the priority is bigger than another number, then it would put it in front of it when sorting. And then after that, it would check by earliest end date, and then followed by earliest start date. And then this algorithm would then sort it as well. And then when you check to the bulk of the algorithm, when producing the solution, it first checks the boundaries. So if you look at the left code, it checks whether or not it's valid. If it is, then it will iterate through it and check inside the other data structure, which is this vector in the bottom, check. So basically it's a Boolean. We set all as false with a length of open to close. So when we iterate through each sorted value, it will first see if it's true or false. If it's true, that means it's already taken, so we just skip it. And then if they're all false, it'll change them all to true, as well as adding it into the answer vector.
So onto the performance analysis of our algorithm. Here we have the time complexity. So the raw time complexity for our algorithm would be O of n log n plus n times n at m. And that's where n is the number of meetings that we have, or the number of inputs that we get from the input.txt. And m is the length of the time interval, which is also the length of our check vector. So if we had meetings from 0 to 10, then the length of m would be 10 because we have 10 hours to work with. Then because we also sort in our algorithm, that gives us the O of n log n. And because we're checking which time slots are available for every input, that gives us the part of the time complexity where it's O of n times n. But of course, it just simplifies down to O of n log n. This line chart that we made, basically we took 5,000 inputs where we start with one meeting of 5,000 meetings, and we record the execution time for every single one of those test cases, and we produce this line chart from it. The execution time is in microseconds, as you can see, and it's hard to tell, but there is sort of a slight curve as you keep going up. For our space complexity, we determined that it was going to be O of n plus m, again, where n is the number of meetings that we have and m is the number of hours. And that's because we're storing all of our inputs in that vector of pairs that Alan mentioned. And we also have that check vector that is of length m. In these screenshots, you can see that we have, our total heap usage, which is around 402 million. bytes. And here you can also see that our peak heap usage is 302 million. And we got these values by using Valgrind.
Yep, as you can see, there's no memory leaks as well. So on to our fourth part of the presentation, we will talk about strengths, limitations, and improvements. So on to the strengths. So as you can see through the presentation, our code has a lot of strengths that are very applicable in the real world. For example, it effectively schedulizes and maximizes the number of non-overlap meetings. So it's very applicable in the real world. Many businesses can use this. It definitely prioritizes the meetings within the given time boundaries. It follows a greedy algorithm, so it prioritizes the most important meetings, followed by then maximize the number of overlap. It also handles edge cases and maintains optimality and efficiency very well. So for example, like as we said, the boundary checker, if it's not within the open and close range, will automatically not consider the meeting. And as I said, it mimics real world business constraints with a fixed time interval. So onto some limitations of a project. Like it's definitely tough. It definitely has some scalability issues. For example, like right now we tested the time complexity of 5,000, but let's say we make it 100,000. We know this isn't like a real world example, but this is still a limitation to consider. So if it was 100,000, the algorithm would definitely slow down significantly. So a segment tree would definitely be useful to improve performance if it was high. However, the number of meetings is usually small, so a segment tree would not be optimal here. Another limitation that our program has is the manual input required. So right now, users must manually input the data into the input.txt, which is definitely is time consuming. There's a lot of risk of human error. So if someone like is about to type it all, they may have one small mistake. That mistake could be devastating and it could have them redo the whole thing as well as find the error. So maybe automating this process would definitely reduce errors and improve usability. Another limitation is the subjective prioritization. So our algorithm has a priority feature, except saying what the priority is determined by user judgment. So misleading or mislabeling a long meeting as high priority can make cause less important, but more optimal meetings to be excluded.
So some bottlenecks that we are going to address of our algorithm, similar to the last slide, we mentioned that our algorithm does run in n log n time due to the sorting that we have to do. And this will, like mentioned earlier, it will significantly slow this function down with large inputs. And also, because we have to check for every input where we can place that meeting, if that time slot is free, um, if the last value is true, then we would waste time looking through the entire check vector, and that would waste O of n time. And of course, if n is large, it would be very detrimental to the algorithm.
hmm So I'll finish the presentation by talking about a few more improvements if we had more time or more information about the problem. So definitely some improvement might be using a segment tree, as I mentioned before, because when Derek mentioned that the thing had to check O of n times, and the last thing could possibly be used already, that's very time inefficient. So if it was a high data set, then using a segment tree would allow it to be in n log n time instead of n time complexity. Another improvement we wanted to do was maybe if you can allow users to input meetings by priority to reduce sorting to O of n log k with the max heap assuming k is less than So if we knew how much each priority is, we can use a max heap, which would definitely improve the time complexity. Another improvement we can do, if we had more time, or another problem with more complexity, was maybe adding meeting room sizes. For example, like 5 people can go to this meeting, which is not basically like another a condition on top of priority. And if there's multiple rooms to host like this business and the expected attendees for real world realism.
So for our final thoughts, things that we learned is we have a better understanding of greedy algorithms and the interval scheduling problem as a whole. Uh, we were able to see the trade-offs because we visualized our time and space complexity, and it helped us begin to think about, okay, what would we want to prioritize, what would be good for a business prioritize, like what would they want to see from maybe a different version of the problem and what that solution might be. And also, because we did the proof of optimality in the report, it also just helped deepen our understanding of why at least this greedy solution will give us the optimal solution. And overall, we would
It
say
was a very valuable
learning
experience in both theory and implementation.
Thank you.
Thank you.